All right, I'm going to show you some things about logarithmic functions. So there's a lot of good information here. So hopefully you take good notes and jot all this, get all this. All right. First thing you have to be really good at is you have to be really good at going back and forth from exponential form to logarithmic form. And so you probably did this before in Algebra 3-4, but generally speaking, the exponential form, would be a to the, actually I don't want to do that thick, a to the y equals x. So that's exponential form. Logarithmic form says, okay, it's going to be log, and then the base is a, so log base a of x, and then that equals the exponent. So logarithm is an exponent, so that's kind of where the things go. All right, another one. Let's say you have 10 squared. You guys know that equals 100. And if you write this in log form, then you'd say log, and then the base is 10, so log base 10 of 100 equals the exponent. So again, the logarithm is equal to the exponent. Number 3, let's say we have 2 to the 5th. We know that that equals 32. That's exponential form. Log form, we would say log base 2 of 32 equals 5. Those are equal, that's the same thing. Number 4, 9 to the 1/2 is the same thing as 3, and that's because 9 to the 1/2 is really the square root of 9, which equals 3. And if we want to write that as a log, then we'd say log base 9 of 3 equals 1/2. Same thing. So now I'm going to try to work the other direction a little bit. Okay. So let's say I give you a log, and I say, okay, log of 7, log base 7 of 1 equals 0. You've got to know how to go back into exponential form. So you take the 7, you raise it to the 0, 7 to the 0 equals 1. So it's working backwards. Let's try another one working backwards. Let's say you have log, and then the base is 2, and it's 1 over 32, and that equals -5. Okay, so we would say 2, that's the base, raised to the -5 is the same thing as 1 over 32. And that's true, because 2 to the -5, it would drop down to the bottom, so it's 1 over 2 to the 5th, which is 32. All right. That's kind of the official definition of a logarithm. Let a be a positive number. So this right here is always a positive number, other than 1. And y equals log base a of x, if and only if x equals a raised to the y. So these are the same thing. Again, this is log form, this is exponential form. And by the way, x has to be greater than 0 all the time. So this right here, it's called the argument. It's also the domain of the function. It's always positive, greater than 0. Never equal to 0, greater than 0, because that's what the graph looks like. If you look at the log graph, it goes like this, and it approaches right here, but it never touches, and it doesn't have an x value of 0. All right. This is kind of showing the connection between exponential functions and logarithmic functions. So exponential, y equals 3 to the x, so I plotted some points. And then if I switch my x and my y, then I get a log function. And you can see if I want to plot some points, for this I actually would choose some y coordinates. So let's say I chose y equals 0. So that would be 3 to the 0 equals x. So x would equal 1. So that's why I'm getting these numbers. So 1, 0, that's what that is. And then I plug in another number for the y. So I could plug in another good one for y, like 3. So plug in 2, plug in, or a 1 actually. So plug in a 1 for the y, that would be 3 to the 1, which would be 3. So 3, 1. That's why we got that point, 3, 1. Another good point for y is plug in a 2. So 3 squared. So that's 9. So that's why I have the point 9, 2 right here. You notice that the x and y is exactly switched because these are inverses of each other, and they reflect over the line y equals x. So this is the line, of course, y equals x. Probably should have that before. So y equals x. All right, cool. All right, let's do an example of solvents and log equations. Okay, notice that they're both log base 6. And what we can do is we can set the arguments equal to each other. So we have 4x minus 5. That's equal to 2x plus 1. We just solve for x. So subtract 2x, add 5 over. So we get x equals 3. And we always have to check to make sure, because sometimes we get answers with these, they don't make any sense. So we really do need to check. So I check, and I plug in a 3 right in for the x. So, check it out and see. Just make sure that the argument's positive. So log base 6. 4 times 3 minus 5 equals log base 6, 2 times 3 plus 1. Let's see, so this turns out to be 7 in there, and that turns out to be 7 in there. We're going to be fine, so it does check out. Okay. You have to be a little bit concerned because sometimes you'll get answers for x, but then you'll plug them in, and it'll give you a negative argument, this part here. And if that's the case, then it doesn't make any sense. All right. Example 2. This one's a little different. We're not going to be setting anything equal because there's not really anything on the right-hand side that has a log. So what you'll do sometimes when you solve equations, log equations, is you'll change it from logarithmic form to exponential form. Notice this is logarithmic form, so we're going to change it to exponential form. So I'm just going to make a note, change to exponential form. Okay. I'm so happy my wand is working better. I put some batteries in it, it's been causing troubles all day. Alright, so I'm going to say base, so 2 raised to the 4 equals x minus 5. See where everything's going? 2 raised to the 4 equals x minus 5. So now 2 to the 4th is 16. So that equals x minus 5. So x equals 21. So that would be my answer. And you kind of check it, make sure it makes sense. Example 3, let's say we're asked to figure out what in the world is log base 4 of 1 over 16. Well, sometimes if it doesn't have an equal sign, it's not really an equation. A lot of times will just make it an equation, and I'll say it's equal to x. I don't know what it's equal to, but it's equal to x, some amount. That helps me because then I can change it from logarithmic to exponential form. So then I would say 4 to the x equals 1 over 16. And then I can try to do what we were doing before. Remember when we tried to make the left side equal to the right side as far as the base goes, so that we could set the exponents equal to each other? So this would be 4 raised to the x, and then, 1 over 16 is 4 squared, right? So this is 4 raised to the x equals 4 raised to the negative 2. And now, of course, we can set the exponents equal to each other. So now these guys set equal to each other. And so x equals negative 2. Okay. All right. Next example. Let's say they want us to do a little sketching of graphs. And that's, again, based upon our transformation knowledge. So, the sooner you pick up that transformation knowledge, the better. So what you're doing is you're basically comparing it with the graph. It's like the graph log base 3 of x. Okay. So you have to kind of know what that looks like. All of them look the same. They just look like this. They just go through the point 1, 0. They're almost identical. Log base 3, log base 4, there's not much of a difference. Okay. Well, if it's a negative x, then what that does is that reflects it. So it's going to be a reflection. It's going to be a reflection over the y-axis. So you used to not be able to plug in these negative numbers, but now it's really the only numbers you're allowed to plug in, because if you plugged in a positive number right here, then you'd have a negative in front of it, and you can't do that because the graph doesn't exist on the negative side. So now the only numbers you're allowed to plug in are negative numbers, and so it actually reflects it over the y-axis. So it looks like this, that blue graph. Then this one, look what that is. That's a shift, right? X minus, what does that do? Doesn't that shift it over a couple of units to the right? So it would go over like this, and really roughly, really roughly it would look like this. Okay. Yeah, something like that. Okay. So this is the red one. Shifted 2 to the right. So now when you think about what numbers you can plug in for this, they have to be bigger than 2. Anything bigger than 2 is okay. Because if I plug in a 2, then I'd have 2 minus 2. That'd be bad. That's not part of the domain. All right, next. There's something called a common logarithm. It comes up so much because a lot of the things we do are log base 10. So we have a button on our calculator for this, and we have a button on our calculator for natural logarithm. So we have log base 10. A lot of times just say log x. We don't really bother with putting the 10 there. And then log base e, we just say natural log of x. So that's the same thing. You can write log base e of x, but most of the time you're going to see natural log of x. Okay. All right, let's try to figure out some values. So let's say log of x equals 1.7959. You want to figure out what this equals. Well, because it says log, that means it's log base 10. So I would say 10 raised to the 1.7959 equals x. So I would just estimate what that is. So I would get the calculator out, and I would say that x is approximately, it says rounded to nearest hundredth. So x is approximately 62.50. What's that? That's the nearest hundredth, right? 10th, 100th? Okay. So that would be the answer. All right. Natural log now. Well, very similar. So we would have e raised to the 4.7 equals x. So just find your e button, and we would say that x is approximately 109.95, I believe. Okay. All right. The Richter scale. Earthquakes, they use the Richter scale. It's based on a power of 10, so it's a little bit misleading when you hear about earthquakes that are, 6, one's a 6.0 and one's a 7.0. The 7.0 is like ridiculously bigger. It's actually 10 times the magnitude of a 6.0. Actually 10 entire, so that's huge. You know what 10 times is? If someone bench presses 100 and someone else benches 10 times that amount, that's 1,000 pounds. That's a huge difference, 10 times. So we're talking a big difference in magnitude. If you had a 4.0 and then you had like a 7.0, that's like 1,000 times greater magnitude. So just remember that when you hear Richter scales of earthquakes. All right, so on to this problem. We use this little equation. It says R equals log I over I sub O. I sub O, I guess, is this like certain little minimum intensity, the least amount of intensity that you can actually detect with their little monitor things they have. So let's say an earthquake intensity is 1 million times the least amount of detectability. So we would say R equals, we're trying to figure out the magnitude on the Richter scale then. So we would say log, and then for the I, we would just plug in 1 million I sub O. And then for the I sub O, we just leave it I sub O. And then what we do is we cancel off I sub O. So we have log, and then we have 1 million equals R. And then we change it, it's in log form right now, so then we change it to exponential form. So this is a log base 10, so kind of ran out of room a little bit, so I'm going to just go here, sorry. So I'm going to say 10 to the R equals, 10 to the R equals 1 million. So then it's just a matter of trying to figure out what do I need to raise 10 to so that I get 1 million. So how are you going to do this? But this is 10 to the R equals, and this is 10, just however many zeros it has. So it has 6 zeros. So this is, on the Richter scale, it's a 6.0. Okay. All right, last problem I want to show you is, well, before this, just I want to tell you about the rate that something doubles. So the rate at which a population or money doubles, I mean, people really do care about this. They want to double their money so they can retire, you know, et cetera, et cetera. So we want to double our money. It has nothing to do with the starting amount. So you might think, oh, I need to have, you know, $50,000 and then, you know, I got to double it. Well, it doesn't have anything to do with the starting amount. So this next problem kind of illustrates that. Consider a population, could be money, the same things, but consider a population growing at 4% continuously per year. And we're going to use this little quirk formula. And so let's plug in some numbers. So we want to figure out how long it takes to double. That's our question. So how long is it going to take to double at 4%? I should write that. Let's see. Question. How long to double the population? How long? That's not really a good sentence, but that's right. How long to double the pop? Okay. So we have our starting amount, we don't even know. And then we have E, and then we have the rate, so we can put that in there, 0.04 T. We don't know how long. And then we want to double the population. So right now it's at Q sub O. We want to double it, so it's just 2 times Q sub O. That's doubling the population. And then they both have a Q sub O, so we can divide by that. So we divide by Q sub O. And that gives us 2 equals E 0.04 T. Now, whenever you're wanting to solve for an exponent like this, it's a good strategy. What you could do is you could either go straight from exponential form to logarithmic form, or you can take the natural log of both sides. So I'm trying to think which one I want to do in this case. I think I'll go ahead and change it from exponential form to logarithmic form. Let me think for a second. Yeah, so I'm going to change it to logarithmic form. So I'm going to say log base E of 2 equals the exponent, 0.04 T. Now remember, log base E is actually the same thing as natural log. So I'm going to say this is the same thing as natural log of 2 equals 0.04t. So all I have to do is divide by 0.04. So I do divide by 0.04, and t equals natural log of 2 divided by 0.04, which I can just do on the calculator. Natural log of 2 is about 0.69, so I just divide it and I get about 17 point, I think it's about 3 years. Okay. Alright, that's how long it would take to double the population if it just grows at 4%. Alright, well, remember that. And last thing, rule of 72. If people want to know how to double their money, actually all they have to do is take 72 and divide it by the percent that they're getting on their money. So if they say, hey, I'm getting, they're giving me 8%, then we just have to divide by 8, and it takes about 9 years to double your money. So it's kind of quick to figure that out. Alright, and I can explain that a little bit more in class, but I think that's good.